Hey, welcome back. In this video, we're going to tackle the idea of inverse functions. Inverse functions, generally speaking, are two functions that do the opposites or undo each other. How we're going to attack this conversation is I'm going to show you two functions that are the inverses of each other. We're then going to generalize the idea of inverse functions and show you how to find the inverse function if you're given a specific function. All right, here we have two functions that are inverses of each other right here. We have f of x equals x minus 4 cubed, and then g of x, which is the cube root of x plus 4. The first things first, and this is not always brought up, but I think this is very important to understand about inverse functions, is that two functions are inverses if on the independent variable they're performing the opposite operations in the opposite order. So to show you here, what we do is we're going to take x and f of x, subtract 4, and then cube it. So we're subtracting 4 and then cubing. What g of x does, it takes the independent variable and is cube rooting, which is the inverse of cubing, and then adding 4, right? So in the opposite order, subtracting 4 first, adding 4 last, cubing last, cube rooting first. The second important thing to state about inverse functions is that if you look at a table of values, so here we'll look at a table of values for f of x and for g of x, importantly what you'll notice is that the inputs and outputs have been swapped, and that's not by chance. That will always be the case. So for inverse functions, how you comparing the table of values for two inverse functions is the inputs and the outputs get swapped. This second statement is incredibly important, and you'll see the effect through these next two statements right here. First of all, because the inputs and outputs are swapped, graphically what that means is the x's and y values are swapped. So now if we look at the graphical representation of f of x and g of x, what you'll notice is they have the same shape. They seem like they're a reflection, and actually they are. Inverse functions, when graphed, are always the reflections of each other over the line y equals x. And two things about this. First of all, again, this statement about them being reflections of each other over the line y equals x is a consequence of their outputs and inputs being swapped. Also, I want to superimpose here the line y equals x, this dotted line right here. And maybe that can help you see right there is that it is clear that if you reflected that image of one of those graphs over that line y equals x, it would result in the other graph. Then the fourth thing to state, and this is really important for inverse functions, is that they undo each other. And what I mean by that statement is this, is that if I inputted a value into f of x and then took that output and plugged that output into g of x, the result of that would be the original input I put in. We recently just talked about composition of functions, and I'll generalize this statement in 1 second. But the idea is if you have a composition of inverse functions, the two functions, the way in which they interact, the fact that they perform the inverse operations in the opposite order, they cancel each other out. To visually state that last statement I just said with the functions as machines idea that we talked about with composition, is that if you input a value, let's say like we input a 2 into the f of x function right there, we get our output and then plug that output directly back into the g of x function. Again, this is the idea of composition. Take whatever comes out of this and plug it into the other function. The statement is we'll get out a 2. And mathematically would say then, whatever f of x did to the number 2, whatever operations it did, g of x would undo that. And importantly, it's not just for the number 2. Any value that you plug into f of x and then plug that output into g of x will output that original input number. So let's just look at that example here real fast. So what this statement is saying in composition notation is that if you took g of f of 2, my statement is does that equal 2? If it is, and if that works for any value that I plug in, that whatever I plug into the inner function and then get the output and plug it into this outer function, I will always get that original one. That will mean these are inverses because they cancel each other out or undo each other. All right, so let's do this. I'm just going to work with this function notation right here. So f of 2 is what I get when I plug in a 2 in for x right here. And so that will be 2 minus 4 cubed. And we're going to see if this ends up being 2. This is negative 2 cubed, so I'm just going to skip one step here. That would give me a negative 8. So in this little picture right here, what's output by f when I plug in a 2 is I get out a negative 8. Now the question is, does this become 2? Let's plug negative 8 into the g of x function. What this becomes is the cube root of negative 8 plus 4. And the cube root of negative 8 is a negative 2. And it looks like we have it. Negative 2 plus 4 is 2. And again, the focus of what I'm trying to say right here is the fact that we started with the 2. I didn't know what the middleman would be, but that once I plugged that into g of x, I knew I would get out 2 because I'm confident that these are inverses of each other. And again, this original statement makes that same statement. I'm describing that same statement as I'm describing right here. If I plug in 2 and then take that output and plug it into g, or if I compose these functions, I'll end up with the original input. Or more generally, what I'm stating is that for all x values, I'm stating that g of f of x will end up being x. Or in other words, we could say that when I compose my inverse functions, I get out the identity function. And actually, this is true if f or g is the outer function. So I could switch this around to say f of g of x that would also output x. Or how about I just show it right here? This is exactly the same statement. If I have two inverse functions, no matter how I compose them, I'll always output the original input of that inner function. All right, those first two functions, f of x and g of x, were just meant to ground us in the idea of inverse functions, but we now need to generalize. Let's first talk about the notation of inverse function notation. To denote the inverse function, we write it like this, f to the negative 1 of x. Importantly here is that negative 1 is not an exponent. It simply denotes the inverse. So this is the notation for the inverse of f of x. So in other words, an original problem that I had with f of x and g of x, I could have written that as f of x and f to the negative 1 of x, or the inverse of f of x. All right, so our second generalized statement is what we actually ended with in our original example right there, and this idea of composition. This is, again, fundamental to the idea of inverse functions. They undo each other. So the statement is that f composed of its inverse of x will always output x, or the identity function, and this is true for all x values in the domain of the inner function here of the inverse. The same is true if we swap roles. It doesn't matter which way we compose these. So in this case, if we put f of x inside of its inverse, we'll always get the identity function, which just means we'll, again, output whatever we originally input. And this is now for all x values in the domain of the inner function, which in this case is f of x. Our third statement is a direct consequence of what we said for that first example, that we swap the inputs and outputs, which leads to this idea of the undoing of each other. But because they have swapped inputs and outputs, importantly, first of all, the domain of f of x is the range of its inverse. And the range of f of x is the domain of its inverse. This is a really sneaky, useful statement that when you look to graph a function's inverse, understanding that the domain of the original function will end up being the range of the inverse can be supremely useful. Or if you're given a function and asked something about its inverse, if you understand the range of the original function, it can help you understand what the domain of the inverse will be. And finally, the last important statement to generalize about inverse functions is that a function can only have an inverse function if it's a one-to-one function. What that means is that every output of the original function is related to only one input. But I want to make the general statement, and I'll step back and talk about that one-to-one part a little bit more. So again, a function is one-to-one only if each output is related to only one input. For instance, just to give an example of this and to say why this is the case. So again, a function can only have an inverse if it's one-to-one. Let's think about f of x equals x squared right here. So we have this function f of x, and the question is it one-to-one? Does each output, is it related to only one input? Well, if we look at the graph and if we consider a table of values real fast, let's just make a small table of values here. Let's just choose some points that are somewhat interesting, like -2, 0, and 2. In this case, -2 outputs a 4, 0 outputs a 0, and 2 outputs a 4. In this case right here, because both -2 and 2 are inputs that are related to the output of 4, we would say that f of x equals x squared is not a one-to-one function. It is a function, but it's not a one-to-one function, and therefore cannot have an inverse on its full domain. If you're looking at the graphical representation of a function and you're wondering, is this function a one-to-one function? Just like we have the vertical line test with determining whether a relation is a function, and again, what that was, we drew a vertical line. If it went through more than one point, then we had an input that had two different outputs, which is absolutely not allowed for functions. But in this case, if we want to know it's one-to-one, again, we're asking, does something like this occur? Because if something like this occurs, then we're not a one-to-one function because we have the same output that's related to two different inputs. In this case, what we can do is we just take a point on the graph, and if we can draw a completely horizontal line, and that goes through two different points, then it means it's not one-to-one. Importantly, does that mean we're completely out of luck? And no, it doesn't. What it means that if we have a function, we're looking at a function, and we'd like to find the inverse of that function, we first have to restrict the domain in a way that on that domain, the function is one-to-one. In fact, what we do with the square root of x is we restrict the domain to only be 0 and positive numbers. So from 0 to infinity. On that domain, it actually is one-to-one. And if you'll notice, if you take this part of the graph right here, let's highlight it with some yellow right here, if this helps visually. So if we take this part of the graph right here, and we don't think about this part, so just f of x equals x squared on the domain from 0 to infinity, that actually does have an inverse, and that inverse is the square root of x. It's taking this part right here, and as we said previously, the graph of the inverse is taking the line y equals x and reflecting that, and you'll see that that looks like the square root of x. Importantly, the reason that a function needs to be one-to-one in order to have an inverse is the fact that the inverse function needs to be a function. If we took this graph right here of f of x equals x squared, and we flipped this graph, reflected it along the line y equals x, that we know that the graphical representations, that's how the graphical representations of these inverse functions match up. This would end up being a parabola that was on its side. And if you envision a parabola on its side, you can see right away that it doesn't pass the vertical line test and therefore not a function. That same conversation again then from a table of values is if we swapped the inputs and the outputs, the domain and the range of a function, you would notice, again we trade places here, that 4, the input of 4 for the inverse of this function will be related to 2 different outputs, which is not allowed for functions.